Today we prove upper triangular form over complex numbers. Proof complex number Cayley-Hamilton. Define generalized eigenspaces. And point at Jordan form like responsible adults. Yes, this is a lot. Apparently one theorem was not enough paperwork for civilization. Let V be a finite-dimensional complex vector space, and let T be a linear operator on V. The word complex is doing real work here. Over R. Rotation by 90 degrees already ruins the party. Complex numbers whose a non-zero V. The n+1 vectors V through T to the nV cannot all be independent. That gives a non-zero polynomial P with P of T applied to V equal to 0. Because the scalars are complex, P factors completely. Then one factor T minus lambda I must fail to be injective. And failing injectivity is exactly the statement that lambda is an eigenvalue. Tiny miracle. No determinant summoned from the basement. Now the first big theorem. Every operator on a finite-dimensional complex vector space has an upper triangular matrix in some basis. Upper triangular means every entry below the diagonal is 0. Half the matrix is finally quiet, which is more than we can say for most meetings. We prove the theorem by induction on dimension. Dimension 1 is not a theorem. It is a sentence wearing a hat. Complex numbers whose an eigenvalue lambda. Let U be the range of T minus lambda I. Since T minus lambda I is not invertible, it is not onto. Therefore U has smaller dimension than V. The subspace U is invariant under T. Indeed, TU equals T minus lambda I applied to U plus lambda U. Both terms are in U. So TU is in U. That little line is the hinge of the proof. Because apparently hinges now do algebra. By induction, T restricted to U has an upper triangular matrix in a basis U1 through UM. Extend that basis of U to a basis of all of V by adding W1 through WR. For each new vector WK, the part T minus lambda I applied to WK lands in U. And lambda WK stays in its own new direction. So every basis vector maps into the span of itself and earlier basis vectors. That is exactly upper triangular form. Once T is upper triangular, we define its characteristic polynomial by reading the diagonal with multiplicity. So Q of Z is the product of Z minus lambda 1 through Z minus lambda n. No determinant needed. The determinant can wait outside and think about what it did. Complex number Cayley-Hamilton says the operator satisfies its own characteristic polynomial. Q of T equals the zero operator. It is enough to prove Q of T kills every basis vector. In fact, a stronger partial product kills Vj. The claim is T minus lambda 1 I through T minus lambda j I, applied to Vj, equals 0. For j equals 1, upper triangular form gives TV1 equals lambda 1 V1. So the first factor kills V1. For the induction step, upper triangular form says T minus lambda ji sends Vj into the span of the earlier basis vectors. By the induction hypothesis, the previous partial product kills each earlier basis vector. Hence it kills their span. Therefore the partial product kills Vj. Multiplying by the remaining factors still gives 0. Complex number Cayley-Hamilton is proved. Now define the generalized eigenspace for lambda. It is the set of vectors eventually killed by some power of T minus lambda I. Ordinary eigenvectors are killed immediately. Generalized eigenvectors are killed after repeated application. Because linear algebra enjoys installment plans. in an n-dimensional space. Using power n is enough. The generalized eigenspace is null of t minus lambda I to the n. The tiny Jordan block already shows why generalized eigenvectors are necessary. J minus lambda I is nilpotent. So every vector in this two-dimensional block is generalized, even though not every vector is an eigenvector. The next goal is a direct sum decomposition into generalized eigenspaces over complex numbers. V should split as G lambda 1 direct sum through G lambda m. One piece for each distinct eigenvalue. On each piece, T looks like lambda times the identity plus a nilpotent operator. Nilpotent means repeated application eventually becomes zero, which is algebraic exhaustion with better branding. Then we choose bases inside those nilpotent pieces and get a block diagonal matrix whose blocks are Jordan blocks. A Jordan block has lambda on the diagonal, ones directly above the diagonal, and zeros everywhere else. So the coming theorem is, over complex numbers, every operator on a finite-dimensional vector space has a basis such that its matrix is block diagonal with Jordan blocks. That is the destination, not diagonalization. Because life noticed we were briefly happy and corrected the error. Today we proved upper triangular form, proved complex number Cayley-Hamilton, defined generalized eigenspaces, and set up the direct sum route to Jordan form. The moral is simple. Complex eigenvalues make triangular form possible. Triangular form proves complex number Cayley-Hamilton. And generalized eigenspaces rescue us when eigenvectors are too lazy to form a basis.